Let's discuss the last three problems from today's Division 2 contest, starting with C. You can read it now or listen to my explanation. In my explanation, we have a series of definitions. First definition is the score of a sequence. We call it the score of a sequence, the product of its elements, divided by the factorial of its length. Then we call the cost of a sequence as the maximal length of a subsequence which has the maximal score. So over all subsequences of this sequence that have the maximal possible score, we take the maximum possible length of such subsequence and call it the cost of a sequence. We are given a non-decreasing sequence. We want to find the cost of all its prefixes. Such problems that deal with such strange new definitions are most of the times solved by exploring the properties of those definitions of those objects introduced in this problem, especially given that this is Division 2C, so it must not be hard. So probably if we just explore the properties of the given functions, we will simplify this problem to something trivial. Let's start exploring. Suppose we have a sequence. Every cross is a number. Let's say it's sorted in non-decreasing order. If so, first of all, we must understand what is the maximal score a subsequence of the sequence can have. First thing that we can do is to draw a potential answer. Suppose the answer looks like this. And I remind you that the sequence is sorted in non-decreasing order. Well, how can we improve it? Of course, given that its length is 4, we could instead take the largest 4 elements. As you can see, the product will increase while the length will be the same. So obviously we can only consider such subsequences which are a suffix of a sequence. Now, let's consider the score of a suffix. The score of a suffix is equal to the product of all its elements over the factorial of the length of the suffix. Let's see how the score of a suffix changes if we add one element. Because this is generally a good idea. See how the score changes when you apply a small change to your object. In this case, the score is multiplied by the value of this element, but in this particular case, divided by 5. Because 4 used to be its length, now 5 is its length of the suffix. And now we divide not by 4 factorial, but by 5 factorial. So we need to divide by 5 more. So we multiplied our answer by this element over 5. If we want to further extend the suffix, we'll multiply the score by this element over 6. We'll multiply this by this over 7, and so on. As we know that the sequence is non-decreasing from left to right, we know that those numbers will be decreasing as we go further to the left, because those crosses do not increase if we go from right to left, but the denominator increases. So, of course, those numbers strictly decrease. So at some point, when first time such number will be less than 1, we will not want to further extend the suffix. If sum of those values is equal to 1, then we don't care. We can take such suffix or such suffix. But here we can remember that among all the possible sequences that have the maximum possible score, we want to take the one that has the maximum length. So in this case, we strictly want to take this element. And so obviously this will be the maximum possible length a subsequence with maximum possible score can have. So this is the cost of our sequence. The cost of our sequence can be defined as follows. If we go from right to left, and we divide the rightmost element by 1, the second rightmost element by 2, by 3, by 4, when is the first time the value we write becomes less than 1? Or for how many elements this value is not less than 1? For how many elements this value is not less than 1 is the score of our sequence. Now let's write it strictly using algebraic expressions. Now let's say we consider the prefix of length k of our original sequence. Then during this process, the ith element will be divided by k minus I when we go from right to left and extend our suffix. Because first one in this process is k minus 1, and it's divided by 1. Second is k minus 2, it's divided by 2, and so on. So obviously the ith element is divided by k minus I. We take the ith element into the suffix if this holds. We can rewrite it as ai is larger or equal than k minus I. And we can rewrite this as ai plus I is larger or equal than k. So now we can simplify the process as follows. We can say that when we consider a prefix of length k, we want to find the leftmost elements of this prefix such that ai plus I, if I is the index of this element, ai plus I is at least k. So what we care about in this problem is the values of ai plus I. We don't care as much about the original values of a. We care about those elements, those values, ai plus I. For each prefix k, we want to find the first such value of I, that ai plus I is at least k. And we know that such element always exists, because for I equal to k minus 1, a of k minus 1 is at least 1, plus k minus 1 it will be at least k. So of course such value always exists on the prefix. And when we find such I, the answer is just k minus I, because we take everything on the semi-interval from I to k non-inclusively. K is the size of the prefix, so if we enumerate from 0, k is a non-inclusive right border. So the size of the suffix is k minus I. So the answer, the cost of our prefix, is k minus I. And now, of course, we need to find it quickly, yes? But this is pretty easy if you see that if we find the answer for k equal to 1, k equal to 2, k equal to 3, and so on, you can see that those values are also increasing. So we can use the 2 pointers method for finding I. So instead of finding this I from scratch for every different k, we can take the answer for previous k and just move it to the right until we find the first I for which it is true. Let's see how I implemented it. We read A. Instantly we switch to ai plus I instead of a. So we store those values instead of our original array A. Then I create the value I, which will be used from iteration to iteration, because I want to use the 2 pointers method. Then for every k, for every length of our suffix, I just see if such element exists and it's less than k, then it means I still didn't find the element I want, because the element I want is the first element on the prefix whose ai plus I is larger or equal to k. When I stop, it means that I found this element and I output k minus I. Now for the problem D, you can read it now or listen to my explanation. In my words, you are given a list of 2n positive integer numbers. You need to find the number of ways to construct a factorization of length n using those numbers. What is a factorization of length n? It's when we write some of those numbers, n of those numbers, and write the other n here. All those numbers written here must be prime different numbers, and they must go strictly in increasing order. And those numbers are its powers, and there are basically no constraints for those numbers. So we can already redefine the problem a little bit by saying that we want to choose n of our numbers which are prime, but we don't get to define the order. The order is determined. It's the increasing order. But for the rest of our numbers that weren't chosen, we do define the order. And so, how many ways are there to do that? This is a combinatorical question, so let's try to solve it step by step. First of all, suppose we've chosen n of our numbers. Obviously, those has to be prime numbers. But suppose those numbers are fixed. How many ways there are to place the rest of the numbers on those n positions? Well, it depends on which numbers we have left. If all the numbers are different, then there are n factorial ways to place those n different numbers on n positions. But some of the numbers may be the same. This is a famous combinatorical question. It's easier to show using an example. Suppose we have two numbers 1, two numbers 2, and one number 3. There are 5 factorial different permutations of those numbers, but not all of them are different. But let's see how many times each different permutation was counted. Each unique image, if you like. For example, let's call this a unique image. Let's call this another unique image. For example, 2, 3, 2, and so on. So there are very many unique images. But each of them corresponds to the same amount of permutations, because these two can be the first two from the original array, and these two can be the second two from the original array, or these two can be the second from the original array, and this can be the first. So the same with those ones. We can place the ones from the original array at any order on those positions. If we place them on those positions, we will still get the same image. So how many ways are there to get such an image? We can put ones in 2 different orders. We can put twos in 2 different orders. So there are 2 by 2 different ways to get such image. And this will be true for every image. Every image will, for the same reason, have 2 by 2 different permutations that correspond to such image. Which means that in this particular case, there will be 5 factorial over 2 by 2. Such many images. Because there are 5 factorial permutations, each image will correspond to 2 by 2 different permutations. So there will be 5 factorial over 2 by 2 different images. So now let's find the general formula. If we have k different values, let's say, the first one occurs f1 times, the second one occurs f2 times, and so on, the last one occurs fk times. And let's say their sum is n. We want to know how many different images we can get by placing those values on different positions. We know that there are n factorial different permutations, but each unique image corresponds to f1 factorial times f2 factorial times etc. fk factorial different permutations. Because when you have an image, you can place the original first values in any order as long as they go on those positions. But the order doesn't matter. So there are f1 factorial different orders in which you can place them on those positions. The same for the second value, the same for every value, and all those ways to put each of the groups of unique values are independent. You can choose any of these many ways in which you place the original values of x, any of these many ways in which you place the original values of y, and so on. So the overall number of ways to get such image is this. So the overall number of different images is the overall number of permutations over number of permutations for that correspond to a single image. So now we know that if we have n values, we can get this many different images by placing them in different order, where n is the number of values and f's are frequencies of different values. So now let's remember our problem. In our problem, we have two n numbers. Some of them are prime, some of them are not prime. Let's break our original elements of the list into groups of equal value. Let's say each group has the same value within it. For example, this is a group of 2s, this is a group of 3s, group of 5s. Some groups will have a non-prime value, 6, 7, 7. The process using which we can construct a factorization, the main object of our problem. The process can look like this. We first of all choose n different prime values that we have to serve as p values in our factorization. Let's say this is prime. So we write 2 times 5 times 7 times whatever. And now we need to place the remaining values in some order at those positions. Let's say the last is 19, for example. At those positions, at those n positions. We know that we have n values remaining. Some of them are equal, some of them are not. So we can now apply this formula to find how many different factorizations we can achieve if we choose those exact n prime values to serve as our p values. Why will this not be always the same? Because depending on which n prime values we choose on the first stage, we get different frequencies of values that remain. And so those number of ways to place the remaining values on those positions will not be always the same for different chosen p values. But let's notice that those frequencies won't be random, and they won't be that different from time to time. Those frequencies will be almost equal to the original frequencies of values in our list. Only some of the prime values will now occur one time less. N of the prime values we've chosen will now occur one times less than in the original array. So let's say that our answer is the sum of those values for all different sets of values p, which I will denote like this. But let's try to rewrite this expression. Let's say that f1, etc. fk are the original frequencies of our k different values from the original list. So how many times each of those values occurred in the original list. But let's know that all the values of f small are either equal to the corresponding f large or less than it by 1. And let's see that fi factorial is either equal to f large I factorial or fi large factorial over fi. So let's rewrite this expression as n factorial over the product of all f large factorials but some of those factorials are divided by their fi, the corresponding fi. So let's write here in the numerator fi1 times fi2 fin. Why n? Because those I1, I2, etc. in are the values, the prime values that we chose to serve as our p values. And now we can see that this is just equal to we can put this expression outside the summation, because this will be the same for every different set of p-values. So now you see the part of the answer that we still have to find is this. So let's have a closer look on what this is. This is, write out all the f's, f large, that correspond to the prime values in our original list. So f j1, f etc, fj m, let's say. So let's say we have m different prime values in our original list. Let's write out how many times each of them occur. Those will be f large of j1, etc, f large of jm. Now this sum is the sum of products of all different possible sets of n of those values. So for all possible sets of n values from this list, we take their product and then we sum such products. This is what we need to find. So now the remaining part of the problem that we still have to solve sounds like this. You have a list of some size, in our case up to 2n, over all possible subsets of those values of size n, take the product of that subset, and take the sum of such products. Let's solve this problem using dynamic programming. Let's calculate dp ij. And those are the new ij's. dp ij will be equal to the sum of all products of elements of our array for all possible subsets of size j. And the parameter I means that we only want to consider the first I elements of the list, which is a very standard technique. First parameter very often just denotes that we solve our problem only for the first I elements of the list. So if you want a mathematical notation of this, it means that those j's must be less than I, there must be j of them over all such possible sets of j different k's. We take the product and sum up such products. To find the dp of ij, we'll just break those sets into two categories. Those that contain the element I-1 and those that do not contain the element I-1. Those that do not contain the element I-1, their sum is already pre-calculated in the value dp I-1 j, because this is the sum, the analogous sum, but if we only consider the first I-1 elements of the array. And the second category is all those subsets that have an element I-1 among the k. But all such products will have a common factor of f I-1. So we can put it outside of the summation. And the remaining expression will be just equal to the sum over all subsets of size j-1. And if we consider only the first I-1 elements of our list, which is just dp I-1 j-1. Using the formula, we can calculate a single value of dpij in of 1 using the previous value we calculated. Let's look at the implementation. Okay, so the first thing I do is find all the factorials up to maximal n modulo mod, modulo the given modulo. Then I find the inverse factorials. If you don't know what inverse remainder means, it's just a technique that we use to divide modulo p, modulo some prime number. If we know a and b modulo p, we want to know a over p modulo p. Then we have the Eratosthenes sieve here to find all the prime values up to max a, which is around 1 million. Then I calculate the frequency of every value in the original list and store it in map CNT. And then I write dynamic programming. I also use the hidden parameter technique here. So my first parameter I is hidden. So initially I store the 0th layer of the DP table when I is 0. When I is 0, it means that I consider only the first 0 elements of the list. Which means that if I take the products of size 0, then there is one such product if you take the empty subset. And the product of an empty subset is 1. So the sum of all products is 1. For all the other sizes, for all the other values of j, there is no such set of size j among the 0 first considered elements. So all these other sums must be 0. Then we go over this map. If the value is not prime, we skip it. Then we create a vector new DP, which will be the new layer when we already consider this new element. We set new DP equals DP by default, so it means that we have already calculated this part for every DP ij. And now we just need to add this part of the expression for every ij where j is larger than 0. Because if j is 0, then this part doesn't exist, because there are no such subsets that include the last element. So for all j starting from 1, I take the value of dp and add a corresponding expression, where fi-1 is the frequency of the new considered value. In my case, it's v. V stands for value, because it's t and value in the map. And then I shift to the new layer. And then you remember, I initially wanted to find the sum of products among all subsets of frequencies of prime values of the original list of size n. So that's why I take dpn, and this is the last layer, so when all the values are considered, times fn, factorial of n, and then I divide by every factorial of v, which is the original frequency, of every value in the original list. And this is the answer. And now the final problem E. You can read it now or listen to my explanation. So in my words, we have a tree and a set of n-1 numbers. We can choose a vertex of this tree, and we want the set of distances from our vertex to all vertices. We want the set of distances to be equal to the given set. But the given set contains only n-1 elements, and the set of distances contains n elements. So we are allowed to add one arbitrary value into the original set, given in the input. As long as we can make it be equal to the set of distances from V, we consider V to be a good vertex. The problem is to find all the good vertices of the tree. First of all, let's notice there are only n possible sets we can make by adding an arbitrary value into the original set. Because it only makes sense to add values from 0 to n-1. So let's try to add 0, 1, 2, etc. n-1. There will be a set corresponding to each of those choices. So there are only n possible sets to which we want the set of distances to be equal to. So let's write out all those sets. 0, a1, comma, etc. a-1. Then 1, comma, a1, comma, etc. n minus 1. And so on. The last one will be n minus 1, comma, a1, etc. a n minus 1. And yes, the order of the set does not matter. So we need to somehow quickly find the set of all distances from V for all possible V, all possible vertices. And then check that for the given V, the set that we get is one of those n possible allowed sets. Of course, to quickly compare if this set is one of the n allowed sets, we can use hashes. And this is a very good idea to use hashes in this problem. The first thing we can do is to find a hash for every of those allowed n sets and put them all into a set of all possible allowed hashes. Then we just need to quickly find the hash of a corresponding set of all distances from V for every possible V. And for every possible V, if we can quickly find the hash of corresponding set, we can just search it in our set. I mean the set in the sense of set of pair, yeah, like in the C++ set. So first of all, let's define our hash. Let's sort our set in non-decreasing order. Of course, there cannot be any gaps. This won't be a valid set, so I won't leave any gaps. This won't be a valid set of distances, I mean. Of course, this can be one of the allowed sets, but we'll never get it as a set of distances. Let's write out the set in the increasing order. Let's just first of all store our set as a sequence, an ordered sequence of frequencies. There will be 2 zeros, 1, 1, 2 twos, 1, 3, and so on. There will be n values here because the largest value we can have is n minus 1. And there will be, for example, 1 n minus 1. Then we take this sequence of frequencies and apply the standard polynomial hash to it. Polynomial hash means that we choose some base number b that we call base. I'll denote it as b large. And we take this number times b to the 0th power plus this number times b to the 1st power plus this times b to the 2nd power, and so on. And this will be times plus this times b to the n minus 1. And of course, this whole sum will be taken modulo some large prime number, which I will call mod. The advantage of such hash is that you can change any given frequency in O of 1 and recalculate the hash. For example, I want to delete one of those values. This means that this frequency just decreases by 1. Which means that to recalculate the hash, I just need to subtract b to the 2nd power. So if I delete one value 2, it means I need to subtract b to the 2nd power. If I delete one value 3, it means I should subtract b to the 3rd power from my hash. If I want to add 2 into my set, it means that I need to add b to the 2nd power into my hash. So very intuitive. So if I want to unite two sets, the hash of their union will be just the sum of their hashes, modulo mod, of course, which is very, very useful. And the last thing that we may notice is if I want to just increase all the values by 1, I can just multiply the hash by b. It's the same as like adding 0 into this sequence of frequencies. So now 0 occurs 0 times, 1 occurs 2 times because I've increased everything by 1, 2 occurs 1 times, and so on. So let's see how can we quickly calculate the hash of the set of all distances from V for every possible V. I will use a technique which I call rehanding. Usually when I apply this technique, I do the following. First of all, I calculate the information, some information, about every subtree of our original tree. And by subtree, I mean if we hang the tree by some vertex, this is the subtree of this vertex, for example. This is the subtree of this vertex, and so on. So first of all, I calculate some information only about a subtree. And then on the next stage, on the second stage, when I start the rehanding, I now calculate the information about the whole tree, but if this vertex is the root. In this case, the information about the subtree that we want to calculate is the hash of a set of all distances from this vertex, vertex v. But if we only had the subtree of v, so in this case, the set of all distances for v, if we only had the subtree of v, is 0, 1, 1, 1, 2, and 4 times 2. So the frequencies, the sequence of frequencies for such set is 1, 3, 4, 0, 0, 0, 0, 0, and so on. Up to n minus 1, this will be zeros. So the hash of this is this times b0, b to the 0th power, plus this times b to the first power, plus this times b to the second power. And those will be zeros. How can we quickly calculate such hash for every v and the subtree v? We can calculate using the smaller subtrees, the subtrees of the sons of v. Let's see, in this case, the hash for this subtree will be 0, 1, 1. The set for this subtree will be just 0. The set for this subtree will be 0, 1, 1. To construct the set for the subtree of v, we need to unite those sets, add 1 to every of those elements, because we used to calculate distances from this vertex in this case. Now we calculate the distance from v. So of course all the distances will be larger by 1. Same for every other set. So we increase the united set, all the elements we increase by 1, and then we add 0 for the vertex v. For all of those operations with the sets that I described, we can recalculate the hash in O of 1. To unite those sets, we just sum up the hashes. To increase all the values by 1, we just take the resulting sum and multiply it by b. To add 0 into the set, we just add b to the 0th power, so we add 1 to the hash. So we can calculate O the dp of v in O of n, where dp of v is the hash for the set corresponding to the subtree of v and distances from v. Now let's get to the second stage. During the second stage, we start the rehanding. We go in DFS through the tree. In our DFS, we pass the additional information about the supertree of v. So if the subtree of v is this, then let's call everything else the supertree of v. As you see, if v is the root, if v was the root, then the supertree of v would be just another son of v. But for every other son, we know the dp, the information that we store in the dp table, the information that we calculated during the first stage. But for this supertree, we don't know this information. So we just recalculate it while we go. So in this DFS, when we go from v to 2, we need to calculate the information about the supertree. In this case, the information that we need to recalculate is the hash of all distances in this part of the tree if it was hanged by v. So we just considered what would be if v was just another son of 2. What would be the dp of v? And we call it the super dp. The super DP is the DP for this additional sum of 2. Let's see how can we calculate the super DP when we go from V to 2. So first of all the distances that used to be in the supertree of V will now still be in the supertree of 2, but will be increased by 1. So let's increase all those distances by 1. Then we need to add all those distances from them to V to the set. Let's imagine V had another sun here. So all those distances from them to V. And to take that, we can just take dp of V, which already contains the hash of the set of all distances from the subtree of V to V. And we just need to get rid of those distances from those points to V. So we can take dp2 and multiply by B and subtract it from dp of V. Why dp2 times B? Because dp of 2 is the hash of set of distances of those points in the subtree of 2 to 2. And we want the distances from those points to V. So we need to increase them all by 1. So we take dp of 2 times B and subtract it from dp of V. The result is the hash of the set of distances of those points to V. Adding this with the old super dp of V times B, we get now super dp of 2. Now when we arrive into 2, we know the super dp of 2, so we can quickly recalculate the dp of 2 if it was the root. What would be the dp of 2 if it was the root? By just adding this one new sun, super dp, super tree. We just take super dp times B and plus dp of 2. That's how we get the desired hash of the desired set, and we just now check if it occurs in the set of hashes of the allowed sets. We check it in all of log. Let's look at the implementation. In my implementation, I use 2 hashes, because using one hash leads to collisions and wrong answers. Let's look at main. This part was needed to find some prime number larger than 1 billion, which I used here as a second modulo for the second hash. For the base, I took some prime number greater than 200,000. Because 200,000 is the largest frequency we can get. Of course, I don't want my frequency to be larger than B. And another prime number larger than 200,000, I call it B2, and I will use it for the second hash. Here I just calculate the frequencies in the original set. Here I pre-calculate the powers of B modulo corresponding mod. And here I calculate the pair of hashes, hash 1 and hash 2, for the set from the input. I take every frequency times the corresponding power of B and add it to the hash first and the hash second. Then I try to add all the possible values from 0 to n minus 1 into the set and see what hash do I get, and add this hash into the set of hashes. Then I read the tree. dp will be the information about the subtree of V. The first DFS is called find dp. In there, I just take the sum of dp's of all suns, multiply them by B. First hash is multiplied by B1, second multiplied by B2, and add 1. 1 is added for V itself, because V itself has a distance 0 to itself. And then the second DFS is called find answer. In this second DFS, I have the current vertex, the parent, and the super DP, the information about the super tree, if it was just another son of V. Here I recalculate the DP of V if super tree was just another son. So I add super DP times B to DP of V and find such hash in the set of all allowed hashes. If I found such hash, I add V to the list of good vertices. Then for every son, I just go into that son, recalculating the super DP. I take the super DP times multiplied by B to increase all the distances by 1. And then add dp of V minus dp of 2 times B. To avoid taking negative numbers modulo some number, I take this product, take it modulo mod, and add mod, so that this sum is not negative. And that's the solution. That's it for today. Thank you very much. And I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram. Goodbye.